Hello, this is the 8th video on my series of multivariable calculus videos. In this video, we're going to talk about arc length of a curve in space. So how do we evaluate the arc length of a curve in space? The way we're going to do that is we're going to assume that we have a parameterization for this curve. Let's say r of t is the parameterization, and the curve is between r of a and r of b, and we're trying to find the length of this arc, length of this arc. So how do we do that? We're going to divide this piece into separate pieces, and we're going to approximate each of these with one segment. So we are going to take the interval from A to B and divide that into n pieces, t0, t1, t2. In this case, this would be r of t0, this would be r of t1, this would be r of t2, this would be r of t3, and finally the last one is r of t4. In this case, we divide that into 4 pieces, and then we're going to evaluate the length of each of these segments, and then we're going to add them up, and then we let the number of segments to go to infinity. So in general, this is what we're going to do. We're going to choose n plus 1 points, which would divide our segment, our curve, into n pieces, approximate each piece with a segment. The length of each segment would be r of t minus r of ti minus 1, and then we'll have to take the magnitude of that. Now, in order to be able to evaluate that, we'll have to approximate that. We get a Riemann sum, and then we are going to turn that into an integral. So let me remind you something from single variable calculus. If you recall, in single variable calculus, we had the mean value theorem, which told us there is a point C that f prime of C is equal to f of b minus f of a over b minus a, as long as our function is differentiable. So what does that mean geometrically? It means if you take a curve from A to B, there's a point in between A and B called point C, that the tangent line at that point has the same slope as the secant line from point A to point B. So this is the slope of the secant line, and this is the slope of the tangent line. So there is a C in between A and B, that f prime of C is equal to f of b minus f of a over b minus a. Now let's cross multiply. We get f of b minus f of a is equal to f prime of c times b minus a. Now going back to what we did here, we have r of t, r of ti minus r of ti minus 1. So this would be equal to r prime of something, I'm going to call that ci, times ti minus 1 by the mean value theorem, by this equality. So that means I can write it down as r prime of c times delta t. Notice that this is really not a rigorous proof. It is more like a justification for why this would make sense. The final answer that we get, it does make sense. Now what we get is this. We get that the total arc length is going to be approximately the sum of magnitude of r prime of ci times delta t. Delta t is a constant, is a scalar, positive scalar, so I can take it out of the magnitude. I equals 1 to n. So we get this. And what is this? This is what we call a Riemann sum. And as we let n to go to infinity, we get an integral. So when we let n go to infinity, we get this integral. So the arc length is the integral of r prime of t dt from a to b. So that's a very important formula that you need to remember. Okay, so let's do an example on this one. Find the length of the curve given by r of t equals cosine t sine t between these 2 points. So for us to be able to evaluate the arc length, we'll have to first find the derivative of position, which is the velocity, take its magnitude, and then integrate. So this would be minus sine of t cosine of t, and then 1. So that's the derivative of r prime, derivative of r. Then we're going to take the magnitude, so we get r prime of t magnitude of that is equal to square root of sine squared t plus cosine squared t plus 1 squared, which is going to be root 2. Then we'll have to find the endpoints. So when r of t is equal to 1, 0, 0, then cosine of t, sine of t, t would have to be 1, 0, 0, and that happens when t equals 0, because we need this t to be equal to 0. So let's look at what happens when r of t is equal to the other point, which is 1, 0, 2t. Well, that gives us cosine of t, sine of t, t must be 1, 0, 2 pi, and that tells us that t must be 2 pi. So the endpoints are 0 and 2 pi. And by the way, this is the same curve that we talked about it last time. It is called a helix. So we are evaluating the arc length of a helix. So arc length would be integral from 0 to 2 pi. Those are the endpoints that we found. Magnitude of r prime of t, which we found root 2 times dt. This would be root 2t from 0 to 2 pi. Then we're going to plug in 2 pi. We get root 2 times pi. Plug in 0. We get 0. So this would be our answer. Now, if you're given a curve and you measure the arc length of this arc from a fixed point r of t0, so at any point t, we're going to measure this arc. This is going to give us a function called the arc length function. So in other words, the arc length function s of t is the integral of magnitude of r prime from a to t. In this case, they told us that t0 is a, so I'm going to just use a for the initial point. Now, by the fundamental theorem of calculus, when you take the derivative of the left side s, you get the integrand. So derivative of s is going to be magnitude of r prime of t. This is the formula I'll be using later in the study of space curves. Okay, so let's do an example on the arc length function. Find the arc length function for the curve given by r of t equals e to the power of t, e to the power of negative t, root 2t measured from 1, 1, 0. So as usual, we'll have to find r prime of t. That is going to be e to the t, negative e to the negative t, and root 2. Next, we're going to take the magnitude of that. So magnitude of r prime of t is going to be square root of e to the power of 2t plus e to the power of negative 2t plus 2. And then we'll have to integrate this. Okay, so in order to integrate this, we'll have to simplify this square root. Now, there is a couple of different ways of simplifying that. The method that most students are more comfortable with would be to do this. So write down e to the power of negative t as 1 over e to the power of negative 2t as 1 over e to the power of 2t, and then take the common denominator. So common denominator is e to the power of 2t. Numerator becomes e to the power of 4t plus 1 plus 2 e to the power of 2t. Now it is easy to recognize the numerator as a perfect square. So that's e to the power of 2t plus 1 squared. And of course the denominator is already a perfect square. Now that this is all a perfect square, we can get rid of the square root, and everything underneath the square root is positive. So we get e to the power of 2t plus 1 over e to the t. Okay, so we have to integrate this, but we have to also find out what's the initial point. So when r of t equals 1, 1, 0, r of t equals 1, 1, 0, that tells us 1, 1, 0 equals e to the t, e to the negative t, root 2t. And that tells us that t must be 0. So the initial point is t equals 0. So the arc length function is going to be integral from 0 to t of this speed. But since I'm integrating and limits of integration are 0 and t, I'll have to change t to some other variable. So maybe e to the power of 2x plus 1 over e to the power of x dx. In order to evaluate this integral, we'll split that into two fractions. So e to the power of x plus e to the power of negative x dx. Now this is easy to integrate. Integral of e to the power of x is e to the power of x. Integral of e to the power of negative x is e to the power of negative x with a negative sign. And then we'll have to evaluate that from 0 to t. We are going to substitute t. We get e to the t minus e to the negative t. We're going to substitute 0. We get 1 minus 1, which is 0. So that would be s of t equals e to the t minus e to the negative t. So this is arc length, our arc length function. Okay, so let's look at the next topic. So in this section, we're going to talk about tangent and normal vectors to space curves. So again, we are talking about space curves. So let's assume that you are given a space curve given by r of t, and we are trying to find the tangent line or tangent vector to this curve. Well, we have talked about this. That basically is given by taking the derivative. But unfortunately, this derivative is not a very good vector because it depends on what kind of parameterization we have. If we only want to create something that depends on the shape of the curve, we would like this r prime to not depend on our parameterization, but only depend on the tangent line to the curve. So how do we adjust that? Well, the way we're going to do that is we're going to take r prime and we're going to find a unit vector in that direction, which means we are going to divide by its magnitude. And this would give us the unit tangent vector to this curve. What is the normal vector? The normal vector is something that is perpendicular to the tangent vector. And again, in order to create something that does not depend on the parameterization, we are going to find a vector that is a unit vector. So now, how do we find n of t? Okay, so I just talked about the unit tangent vector. T of t is r prime of t over magnitude of r prime of t, which is just velocity over speed. So before I talk about how to find the unit vector, unit normal vector, let's do an example on finding tangent vectors. Okay, so find the tangent vector to the circle of intersection of the plane z equals 5 and the cylinder x squared plus y squared equals 4. So in order to be able to find the tangent vector, we'll have to first find a parameterization. So r of t equals, well, x and y satisfy x squared plus y squared equals 2 squared. So that would be 2 cosine of t, 2 sine of t, and z satisfies z equals 5. So that would be our position vector. Next, we're going to have to find the velocity. So r prime of t is going to be minus 2 sine of t, 2 cosine of t, and 0. So position is x, which is 2 cosine, y, which is 2 sine, and z, which is 5. Now the tangent vector, which is the unit tangent vector, is going to be based on what we just talked about, r prime of t divided by magnitude of r prime of t. So in order to evaluate that, we need to first find the magnitude of r prime of t. So let's do that first. Magnitude of r prime of t is going to be square root of 4 sine squared of t plus 4 cosine squared of t. So when you factor 4 from here, we get 4 sine squared of t plus cosine squared of t. And we take the square root of that. And that would be square root of 4, which is 2. So we will have to take the derivative of r, which is negative 2 sine of t, cosine of t, 0. And then we have to divide by its magnitude. But this answer doesn't make a lot of sense because the original question did not have a t in there. The question was find the tangent vector to the circle of intersection of these two. And the answer would have to be in terms of x, y, and z. So we need to change this to x, y, and z. So how do we change this to x, y, and z? Well, let's look at what we had. We knew that 2 sine is exactly y. So this would be minus y. And then we also knew that 2 cosine is exactly x. So that would be x and then comma 0 divided by 2. So in other words, the unit tangent vector is going to be negative y x 0, and of course we have to divide that by 2. So this would be the unit tangent vector. Now let's understand the unit normal vector. Well, if we look at the unit tangent vector that we just talked about, its magnitude is 1, which means the dot product of this vector in itself is 1, because if you recall, the relation between a vector, magnitude of a vector, and the dot product was this. U dot u is the same as magnitude of u squared. So if we write down t dot t is equal to 1 and differentiate both sides, we are going to get t prime t plus t t prime equals 0, because derivative of 1 is 0. And because the dot product is commutative, we get 2t prime t is equal to 0. So that means t and t prime are in fact orthogonal or perpendicular. Orthogonal and perpendicular are the same thing. So if we graph this one, we have a unit tangent vector, which we'll talk about it. We talked about it earlier. And then we also have a unit normal vector. The unit normal vector is in this direction. So we know that the derivative of t is perpendicular to t. So that means if I want to find the unit normal vector, I'll have to take the derivative of capital T and then divide it by its magnitude. So let's do an example on that. Find the tangent and normal vector to the curve given by this at point 2, 0, 0. Okay, so in order to find the tangent vector, we'll have to first find the derivative of position, then we'll have to take its magnitude, and then we'll have to divide them. So r prime of t is minus 2 sine of t, 2 cosine of t, 1. Then we'll have to find its magnitude, and then we'll have to plug in the value for t. But in order to simplify things, we could first find the value of t so that we don't have to take the magnitude of this one, which is a little bit more complicated, although not by a whole lot. And then we're going to plug in t, and then we're going to take the magnitude. So when r of t equals 2, 0, 0, then 2 cosine t, 2 sine t, t must be 2, 0, 0. But that means t must be 0. So let's evaluate r prime of 0. R prime of 0 is going to be negative 2 times sine of 0, which is 0, 2 cosine of 0, and then 1. And then let's take the magnitude of that. Magnitude of r prime of t at r prime of 0 is going to be square root of 0 plus 4 plus 1, which is root 5. So that tells us that the tangent vector at 0 is equal to r prime of 0 divided by magnitude of r prime of 0, which means we'll have to take the vector 0, 2, 1 and divide it by root 5. So it would give us this vector. So the answer for the unit tangent vector at the point 2, 0, 0 is 0, 2 over root 5, 1 over root 5. In order to find the unit normal vector, what we're going to have to do is we're going to have to find the tangent vector at any point t, and then we have to take the derivative of that. So this is going to be r of t divided by r prime of t divided by magnitude of r prime of t. Okay, so we already evaluated r prime of t. R prime of t was negative 2 sine t, 2 cosine of t, and then 1. So we evaluated that at the very beginning. Then we'll have to divide it by its magnitude. So it would be 4 sine squared of t plus 4 cosine squared of t plus 1. Now, what is 4 sine squared plus 4 cosine squared? That's 4, because if you factor of 4, you get sine squared plus cosine squared, which is 1. So that would be root 5. And then we have negative 2 sine t, 2 cosine t, and then 1. Next, we're going to have to take the derivative of this. So t prime of t. So this would be minus 2 cosine of t minus 2 sine of t and then 0. And then divide by root 5. So now the normal vector would be this guy divided by its magnitude. But let's evaluate that at the point 0. Why do we evaluate that point 0? Because they told us r of t is 2, 0, 0, and we figured that t equals 0 gives us that point. So we're going to evaluate that at t equals 0. We get minus 2 cosine of 0, which is 1, 0, 0, divided by root 5. That's t prime of 0 at that's t prime of 0. Now we're going to find the magnitude of this. Magnitude of t prime of 0 is going to be square root of 4 plus 0 plus 0 divided by root 5. So that would be 2 over root 5. So this means n of 0, which is the normal vector at 0, is going to be t prime of 0 divided by its magnitude, magnitude of t prime of 0. Now, we take this vector and we divide that by 2 over root 5. So if we divide that by 2 over root 5, we're going to get negative 1, 0, 0. So this is the unit vector at the given point. To summarize, what we did was we talked about the length of a curve, which is given by integral from a to b of magnitude of r prime of t dt. Arc length function is given by integral, the same integral except that the upper limit is going to change to a variable t. To find the normal tangent vector, we find the derivative of the position divided by its magnitude. To find the normal vector, we find the derivative of the unit tangent, and then we divide that by its magnitude. So that brings me to the end of this video. I will see you in the next video.